Okay. So last lecture, we saw the graphical method, which is really taking an equation and graphing the right side and left side and literally finding out where the two curves intersect. And depending on with what resolution we build the graph, it will give you an answer closest to that decimal point. So if, for example, we built our graph with a table in which the x value was varied in steps of 0.25, the root or the answer that you find will be good to 0.25 divided by 2. That is, the maximum resolution error is half of the resolution. So let me write that down. It's something you want to definitely remember. So in this case, for example, we are solving exponent of minus x equals cosine of 4x. And our step length is in the range of 0 to 8 pi. Or 0 to 4 pi, sorry. 8 pi? Okay. X varies from 0 to 8 pi. Our step length was 8 pi minus 0 divided by 100, or about 0.251 to 3 decimal points. This is what we call the resolution of plotting in this case. The solution is good to within half the resolution. Half the resolution. So if I call this R, the error is R divided by 2. You can increase the resolution. That just means more intervals into which you chop the 0 to 8 pi. You can make this 1,000 or 10,000 depending on how fine you want to go. Okay. So you have this. Okay. You have a graph, and I'm going to do a few things here. Let me write this here. Focusing on the interval 0 to 5. I'm just arbitrarily cutting it off at 5 because beyond 5, I find that one of my functions is just practically 0. So we'll just focus on the roots that can be found between 0 to 5. We find that there could be a root somewhere between, if I say between 1 and 1.5, would you agree? Would you? Between 1 and 1.5. And there could be a second root somewhere between 1.5 and 2, closer to 2. And I'm going to just use my judgment and say, if this is halfway, this is 3/4 of a way, it's between 1.75 and 2. I'm just eyeballing this. Between 1.75 and 2. And a third root may be seen, can we say between 2.5 and 3. A fourth root is found right around 3.5. I don't know whether it's lesser or higher, looks like higher, but I'm just going to conservatively say between 3 to 4. And then one more root, I'll call it x5, is seen between 4 and 4.5. We are all together so far? Good. So this is sort of like getting to use a classic American phrase, getting the ballpark estimate. It narrows it down to between 1 and 1.5. Now you want to get a precise answer. Now you want to get an exact number which will satisfy the equation and lies between say 1 and 1.5. I'm talking about this root right here. There are two ways to do that. The first way is the simpler way. The simpler way is to just use the lookup table, look up the table which was used to graph the function in the first place. So if you go back to the table, we know our root lies between 1 and 1.5. So I'm going to highlight between 1 and 1.5. We have 1, at which point the difference was negative, and then 1.5, at which point the difference is positive. Now, what is this difference? I'm sorry, that is the function, not the difference. So I want to compute difference between the two functions, that is LHS minus RHS. Okay, and let's focus on this. I'll give you time to write. So please listen now and write. At x equals 1.005, the difference was positive. And what is the difference? It's exponent of minus x minus cos 4x. So let me write that here. Please, no need to write, listen, okay? The difference is defined as e power minus x minus cos 4x, LHS minus RHS. If difference is positive, what does that imply? It means this function was larger. Okay, at x equals 1.005, difference was positive. At x equal to 1.508, difference was negative. Yes. No, we care about the sign. We care about the sign. Who said anything about not caring about the sign? No, there is information in the sign. All right. So look at this and tell me what does it mean graphically for the function to have a positive difference at 1 and a negative difference at 1.5. What does that mean?
They have to intersect at some point.
They have to have crossed each other at some point, right? That's literally what happens, where if you see here, until this intersection point, e power minus x was above this curve, and after that intersection point, it came below the curve. That's what the flipping of the sign means, that there was an intersection between 1.005 and 1.508. This flipping of sign implies an intersection happened. And that's what we want to narrow down. Now, if you just look at the table and go by this 3 values, the best you can do is your answer, you would say, is 1.257. You would just look at the middle value. There, the difference is the smallest with a negative sign, and you would call this your root. So a very crude estimate, is x equals 1.257. Are you with me so far? A very crude estimate is to take your table and just take this middle value, which has the minimum difference, and call it your root. We can do better. We can do better if you just look at the first 2 entries. At 1.005, the difference is positive. At 1.256, the difference is negative. Now apply the same logic and make the next statement for me. If you just focus on these first two rows, what does that tell us? There must be an intersection point that lies between 1 and 1.257 or 1.005 and 1.257 because the sign is flipping right here. Is everybody seeing that? Between these two, there must be a root or there must be the intersection point, right? So there is nothing that prevents us. I'm going to make a copy of this sheet and put it here, and I'll call this bisection example 2. Focus on this, okay? I'm going to make this row bold, and I'm going to make this row also bold, and then I'm going to add one row here, and let me take the average of these two. That is between 1 and 1.25, you will have the midpoint, right? Let me choose the midpoint and put it here. I want to select the first entry and the second entry, the average of those two. And then I can copy these. Did that make sense to you? I just took the midpoint of 1 and 1.25, evaluated x at that value. Wait, this x. Yeah, I don't need this anymore. Oops, sorry. Give me 1 second to fix this. Yeah. So I don't need this anymore. Just going to, oops. Yep. All right, here I'm going to label this newly added midpoint. Are you with me? We added a midpoint. At that midpoint, the function's value left hand side 0.322, right hand side minus 0.187, and the difference is 0.5101. Okay. Now look at the newly added midpoint and 1.25. Apply the same logic, 0.51 positive minus 0.02 negative. What does that mean? There is another intersection between the newly added point and the next point, 1.25. Does everybody agree with that? Right? So now we'll add one more row and we'll calculate the midpoint between 1.13 and 1.25. Oops, I have to divide by 2. And then I'm going to paste it here. So instead of calling it newly added midpoint, I'm going to call it first iteration, second iteration. So my second iteration, 1.19, LHS, RHS, the difference is 0.24. Apply this logic. Between 0.24 and minus 0.02 must be another intersection, or the intersection, you're just narrowing it down. Do you notice that you started with 1 and 1.5, you have squeezed it into 1 and 1.25, then you made it 1 and 1.19. I'm sorry, you made it between 1.3 and 1.25. Now you are saying it's between 1.19 and 1.25. You are tightening the radius and narrowing it down to a very small range. Okay. So between 1.19 and 1.25 must be another root. If there is anybody right now who's not able to see that, you need to speak up. If you didn't understand this at this point, that you are able to see, not see this, you need to speak now. So everybody gets this. Well, we'll see that in the exam. But your silence is basically license for me to assume that you get this. Okay. So 1.19, 1.25. Squeeze it even more. So add one more row. We'll call it third iteration. And the third iteration has to be the midpoint of 1.19 and 1.25. And turns out, at the third iteration, the difference is still positive. You good with that? So then we'll do a fourth iteration, narrowing it even further. You're already if you can see that your interval has gotten really narrow right now. It's only a difference of 0.03. A difference of only 0.03. You started with a difference of 0.5. From 50 units, you have narrowed it down to 3 units. Okay. So then we'll get one more midpoint. So you're now at 1.24. Right? Is that correct? Did I do that correctly? Yeah. You're at 1.24. So between 1.24 and 1.241 and 1.257. So let me make all this down to fixed number of decimal points. Oops. So if I just make this to 3 decimal points, I'm between 241 and 257. And then I'll go to a fifth iteration. That is now the difference is actually very small, 0.007. The absolute difference between, I shouldn't use the word absolute, the difference between the LHS and RHS is 0.007, whereas at 1.257, it's slightly negative, minus 0.02. Now, question is, where to stop or when to stop? How many iterations is good enough? Somebody, any thoughts? You will never get it flip to exactly 0. You will not get exactly 0. So right here, between 1.249 and 253, you are having it flip from 007 to 008 with a negative sign. So now is where precision comes. If you want your difference between the two sides to be less than, say, 1000, if you want this number to have 0, 0, 0 and then something, you need to keep working. If you want the difference to be to 100, that is, if you want 0.00 something, you're already there. Okay. So now, so which will you call as your root? Is it this or is it this? Sorry? Fifth or sixth? Fifth. So if our criterion was to minimize, we can write the statement two ways. So in numerical methods, as you will find out, in this class as well as in your laboratory courses, it's not enough if you punch and crunch numbers. You will have to make a statement at the end stating what your conclusion is. So I'm going to state a conclusion saying x equal to 1.249. Okay, x equals 1.249 to 3 decimal places. 3 decimal places and with error less than 0.01. When I make that statement, my error here in the 4th iteration was 0.04. In the 5th iteration, it is less than 0.01. If I make that statement, 5th iteration or 6th iteration, both of which would actually can be called roots. Okay, so you can also write x equals 1.253 to 3 decimal places and with error less than 0.01. And since your error can be positive or negative, you can write the absolute value of the error is less than 0.01. There is a third way to state this. You can write x can be anything between 1.249 and 1.253, which leads to error less than 0.01. So the implication is you can never really get exact value, but you can narrow it down to a range which is small enough so that you can practically call it an exact value. Questions? So I'll give you a couple of minutes to write this up, and then we'll try one more root finding exercise with this bisection method. Bisection. Bisection method. So let me try to give you a analogy which will make it easier for you to remember this. I'm sure all of you have played Angry Birds, the video game. When you play Angry Birds, your brain is literally doing bisection method. You overshoot, you correct, then you undershoot, you correct until you get the hit. Or if you are at the athletic type and you have done shot put, ball throw or disc throw, javelin throw, you aim for a spot. You need to do this. That's why practice is so important in athletics. You have to practice. You have to understand how much power, angle, wind speed, everything you have to factor it in your head. And your brain is actually a better computer than you are. It can actually figure out all of this by practice. It will take the input of the feedback, how far off from your target you hit, and then correct for it and get it right. And can you give one more example where your brain does this bisection method in everyday life? In all kinds of sports which involve throwing, one way or the other, this is done. The other example I would say is when you are navigating a turn, a curve, your brain is constantly compensating for the curvature, for the banking, for the speed, the acceleration, and whether or not your brain is able to sense your car will trip or not. If you do this too fast, of course, something bad can happen, but your brain is constantly trying not to have that by kind of balancing between acceleration and brake. Or I should say acceleration and deceleration. Most of the time, probably you'll just take your hands off the gas or legs off the gas, and the speed corrects itself due to the friction on the road. All right, so now that you have written this, I want you to take the next root, which is somewhere closer to 2. I want you to apply this bisection method on pencil and paper. That is, you're going to do this on your, not on your laptop, but on pencil and paper, and then get me the root. While I do it on the computer and just look at you like I'm very smart. Pencil and paper, because in the exam you are going to do this in pencil and paper, not with Excel. Okay. I'll have the answer ready. Give you a starting point. Okay. The starting point is the starting point is this, or starting guess at x equals x equals 1.759, 1.759, the LHS RHS difference. LHS happens to be 0.172, 0.729. And the percentage difference is minus 0.5568. And at x equals 2.011, LHS is 0.104. Wait, did I get that right? No, 0.134. 0.134 minus 0.187. 134 minus 0.187. And the difference is 0.3213. 0.3213. So clearly, there is a root between 1.759 and 2.011. Now you narrow it down so that the difference or absolute value of the error is less than 0.01. This is your stopping criteria.
What is the question for, like, in front of how it would be?
Say it again.
What is it asking for? Like, in the question?
We are trying to solve the roots of this. On the question, solve for the roots of the equation e power minus x equals cos 4x in the interval 0 to 5. We just did the first root. So this is into the first root here. x1 1.253, 1.249 for absolute value of the error being less than 0.1. I'm asking you to figure out the second root, which is between 1.759 and 2.011. While you do this with pencil and paper, doing this on Excel, saying so that you feel bad. So if you are already doing it by yourself, continue. For those that are struggling to get started, follow me. Okay, if you are already doing it, you're good. Okay, no need to look up. So iteration 1, we know that the root is between 1759 and 2011. What's the first step? Take the midpoint of these two, right? The midpoint of, say, now x equals 1.759 plus 2.011 divided by 2. And what is that? 1.885, right? 1.885 down to 3 decimal points. I'm rounding off the last decimal point. And at 1.885, the left hand side, which is e power minus x, is what? 0.152. And the right side is cos 4x. I have it here, 0.309, but I want you to, if you have written down something, say that. So the difference would be what? Difference would be, the magnitude doesn't matter, the difference is negative. Are we good? You're able to follow? Those who are looking up. So it's negative here, it's also negative here, so it helps you. It will help you if you visualize this process. Here is 1.759 and then here is 2.011. At 759 this is negative, at 201 this is positive, the difference. So we figured that the root has to be somewhere in between, which is 1.885, and at 885 it is still negative. Okay, what does that mean? It means this range is no longer in play. You can forget about anything below 1.885 because you have narrowed it down between 885 and 2011. You see that? So no, the root cannot be here. If your final answer somehow happens to be here, something went wrong or a mistake. All right, between 885 and 2011, there has to be a root. So iteration 2, x has to be 1.885 plus 2.011 divided by 2, which is how much? Thank you. 1.948. And at that 1.948, e power minus x is how much? Right hand side is how much?
0.142.
0.142, and right side is
0.062.
0.062. That difference certainly looks positive, right? That difference looks positive. So then, if I pick the midpoint, I have 1.948. At 1.948, the difference is positive. And now which part of this range is now no longer in play?
To the right of
Anything to the right of 1.948 is not relevant anymore. So that goes away. Those who are following this, you're with me? If you're not, please ask questions. Yes,
I'm not getting the right hand side.
you're not getting what?
The right hand side values.
0.62. You need to just check your calculation because my Excel also tells the same. Degree or radian?
Okay.
Alright, listen people. So now we have 1.885, 1.948. We'll find another midpoint. So the third iteration would be the midpoint of those two. Can you tell me the midpoint of this and this? 1.912? 1.912, are you sure?
917.
Yeah, that's okay, small difference, 916. Alright, at 916, what is the LHS, RHS and difference?
0.14712 and 0.18687.
18687.
Yes.
So the difference is
Negative.
starting to be negative. Is everyone following? When I try to do examples on the board, you can see me being rushed. That's usually because there is so much to say and so little time to say it. But I'm just trying to speed things along. If you want me to slow down, you always are welcome to say, can you please slow down or wait for me to catch it. All right, 948, 916. 916 is here. At 916, we have negative. At 948, we have positive. So now what? Anything to the left of 916? No longer relevant. So all this is gone. We have now narrowed it down between, I'm going to zoom in and write, this is 1.916, this is 1.948. Look at it, it's just 32 thousandths different. So you're shrinking the range. At now the fourth iteration. Okay, so we have to do the fourth iteration, which is going to be the midpoint of 916 and 948. Fourth iteration, x equals 1.916 plus 1.948 divided by 2, You need no calculator to do this because this is 1.932. 16 and 48 average is what? 32, right? Right? Yeah. So this is 1.932 and the LHS value, RHS and difference. Now you want to start paying attention to the values because you are now entering fourth iteration or so. You might be getting closer to your desired accuracy. What is LHS?
1.145.
0.145. And then right side
1.122.
1 to 2. So the difference is positive, and the difference is actually 0.02. Yeah, do something.
Yeah.
Yeah, can you tell me in 3 decimal points?
Those numbers there is 0.23, 0.023. Yeah.
2, 3.
Yeah.
Sorry? Okay. Let me check with my.
Well, I had some rounding errors and got 1.933.
All right. Let's standardize this. When we are doing intermediate steps, always compute these things to at least 4 decimal points so that there is no confusion. Okay. Okay. That's okay. So then we have 0.023. Okay. So 932 is here, 1.932, at which the difference is positive, and 948 is also positive, which means this goes away, and you're left with 916 and 932. 1.916 and 1.932. Okay. Fifth iteration. What is x? The midpoint of 16 and 32? 24. 1.924. Left side, right side difference.
Left side's 0.146.
Right side is
0.157.
0.157. Difference between is 1 minus 0.11. Okay. Minus 0.11 is also what I get using Excel. Okay. All right. So what does that mean? Here is 924. 1.924, at which the difference is negative. So 16 and 24 both are negative. So between 16 and 24, the root does not lie. So you have narrowed it down between 24 and 32. Right? Everybody. Now, if you are lagging now, you can speak up because this will just compound if you just are not able to follow. So please let's resolve it right now. Anybody not clear what's going on? Yes.
When we get to the third iteration, why do we do 1.885 plus 1.9485? I see you get 1.916. Is it because the sign changed from negative to positive?
Yeah. Yeah, that's exactly right. 24 and 32. Average is what? 28. So x equals 1.928. And left side, right side difference.
Left side 0.145.
Okay, thank you.
Right side 0.142.
So this is now positive difference.
Yeah.
0.003. Right. So now I'm going to zoom in further. Okay. 1.924, 1.932, and then I have 1.928. Negative, positive, positive. So positive at 932, positive at 928, negative at 924. So this is no longer important. So now we have narrowed it down to 0.004, within 0.004. Between 24 and 28, that's where the root is. So seventh iteration, x equals 1.926. The reason I'm going for a seventh iteration is, although this is below 0.01, this still isn't. Okay. So at 926, what happened? Left side, right side difference.
The difference is negative 0.003.
Negative 0.003. Put your pencils down and listen. At 926, it's negative but less than 0.01. That is, the absolute value of the error is less than 0.01. So is here, absolute value is less than 0.01. So I can write a statement like 1.926 less than x2 less than 1.928 for the absolute value of the error to be less than 0.0. There is a root, any number you pick in this range is a root. If you apply the criterion to be, error should be less than 0.01. You might call 1.927 as the root. I might call 1.9275 as the root. They are all similar with regards to the error criterion. This is a nonlinear equation. There is no one exact root. You can only narrow it down to a certain resolution depending on what your application is. Does that make sense? There is no one correct root. If you write, say for example, in the exam, you present this answer like this, that is acceptable. You pick something, say x equals 1.927 as your root with justification that it has to be something that came out of your iterations. You can't like plug it somewhere arbitrarily. If it came in your iterations, you can pick one value. Say for example, you can pick this value and call it a root, or pick this value and call it a root. But it has to be at the end of it, you have to make a statement committing what your thinking is. You give an ambiguous answer and ask me to interpret it, I will interpret it in the least favorable way for you. Okay, does that make sense? You have the present tense. All right, good. So now that we have seen bisection, let me quickly show you my solution with the Excel. So here is my iterations. 759, 2.001, that's where we started. First iteration, 885. Second iteration, 948. I try to do that I try to add a row whichever is closer to that number. Okay, that's why second, third, fourth, fifth, sixth, seventh. So I stop between 926 and 923. Okay, yes.
So for your sub answers, what were around these 4 decimal places?
I will put that in the problem. But in an exam situation, if I say I need the answer to 6 decimal points, that will take you like many iterations. So I'll try to choose a number that's reasonable, like 3 or 4 typically. Yeah. But if it's a homework problem and it's driven by some kind of application, that application may dictate you require it for 6 decimal points or whatever. One example that I often use is if you are in charge of aligning, say, a laser with some satellite, and you are supposed to get the angle right. Well, right doesn't mean absolutely right. You have to get it right to a reasonable degree of accuracy. Now, if you make a mistake of, let's say, 1 part per million, that doesn't sound too bad. But if you have to travel, the light has to travel for 1,000,000 miles, then that's starting to look bad. So you can't always select your error criterion arbitrarily. It has to be tied to some real world application. Okay, so we'll try to emphasize those in the word problems. All right, so you see here, you have your convergence, and this is your final answer, okay? Any questions before we move on? Okay, so let me ask, are you comfortable with this method enough that we can go to the next technique, or would you like to see one more example? Okay. Different example, okay. All right. All right, let's do this problem. Determine the real roots of f of x equal to minus 26 plus 85x minus 91x squared plus 44x cubed minus 8x power 4 plus x power 5. Very messy. Very messy. So first thing is, this is a polynomial, fifth order polynomial at that. So it is going to have 5 roots, okay, that you know from your algebra. 5 roots are going to be there. If there is a possibility that 0, 2, or 4 of them could be complex roots, and there has to be at least one real root. Because it's an odd number, complex roots always occur in pairs, you know that. So there could be 0, 2, or 4 complex conjugate roots. If you are going to apply bisection method or the other techniques which we will see, I would definitely encourage you to start by plotting this. Of course, when you have Excel, when you're doing your homework, you can do that. In the exam, if I ask you bisection method, usually I'll tell you what is your starting interval to guess. That I'll provide. That is, exam is never a representation of reality. It's highly adopted situation. But if you're trying to use this method to solve some engineering problem, you should always start with the graphical method. That's your first step. Okay. So step 1, start by graphing the function in the range of interest. In this problem, we don't know what is the range of interest. We just said determine the real root of this function. You'll have to plot it and see where the function actually crosses 0. So there has to be some trial and error here. There is no, I can't magically predict where the root will be or where it will intersect 0 or whatever. I can't predict that. Okay. So let's use our sheet and try to do the graphing. Okay. And here is where I want you to be clever and build a sheet that can work for any problem, not just a particular problem. we don't know what is our range of interest. Okay, listen for some time, no need to write. We don't know what is our range of interest. Just take, for example, if you put x equals 0, you get what? Minus 26. Suppose you pick a value like say x equals 1. I'm just starting the trial and error. X equals 1, what is your function going to be? Is it positive or still negative? Positive. That is a clue. So between 0 to 1, there is a sign flip. Okay, it just happens to be very simple, 0 to 1. So we'll start with x min equal to 0 and x max equals 1. Okay. Now, if this is my function, I'm trying to determine the real roots of f of x equal to 0. So my left side is f of x, right side is 0. So in order to keep my program still very general, I'm just going to write LHS is the function that I'm interested, minus 26 plus 85x minus 91x squared plus 44x cubed minus 8x power 4 plus x power 5. This is just I'm writing for my own reference so that I know what formula will be punched in subsequent course. What is RHS? What is the right side? 0. Simple. So just put 0. And difference, you can call this difference equals LHS minus RHS. This is just some practice I have. I label the column headings with whatever formula is going in so that later I can recover and see what went wrong. Otherwise, I would have no idea. All right, good. So I have my x from 0 to 1. Of course, I added some iterations which I don't need now. I'm going to delete those. All right, so I have x starting at 0 and then x going all the way to 1, okay, in steps of 0.01, okay. You're with me so far? So next step, you punch in the formula for LHS equals minus 26 plus x or 85 times x minus 91 times x squared plus 44 times x cubed minus 8 times, oops. Four plus x power 5. Right side is just 0 and I drag this all the way down. Told you just listen, don't worry about writing too much. I'll give you time. So it starts at minus 26. It reduces. At some point, there is a change in sign right between 0.55 and 0.56. You can see that right here. And then it goes on, becomes more positive as it goes. So right here is a root. Everybody is agreeing to that. Between 0.55 and 0.56, the sign changes. Wait, hold on. Oh, this is yeah. The function itself changes sign. Oh, this is a mistake. The right side has to be just identically 0. So right here, if you see 56 and 57, went from minus 0.13 to 0.05. So there is a root between 0.55 and 0.56. Now I'll give you time to open and you have your laptop with you, open an Excel sheet and do this, and then we'll do the iterations together. Give you a couple of things together. Or if you don't have your laptop, try to do it on pencil and paper. Those who are trying on Excel, try to recreate this. Those who are trying on pencil and paper, you may start doing your iterations. The main thing is I had my setup ready. I had a Xmin, Xmax, number of steps, step length, and I had this counter and a way to generate X from 0 to 1, all of that kind of already set. That's why I was able to do this very quickly. You can go to the class Canvas page. I can upload this. I have already uploaded this. I can take that as a starting. Next lecture, we'll do this in MATLAB. Sorry? Louder, please. X value. You want it or you want it? I think a lot of people want to know that we do it. So I'm going to do this from scratch so that people can follow with me. All right, you can open a new sheet. We are going to do this again, okay? First, you want to start your Xmin, which happens to be 0 for this problem, and then Xmax 1. And I'm making a choice that I want to divide this interval 0 to 1 into 100 fragments or n fragments. I'll say n equals 100. And based on this, a step length is X maximum minus X minimum divided by number of steps. Type this up. Min, max, number of steps, and then step length or resolution. And then I'm going to have a counter, okay? Counter. Actually, I don't even need a counter. I'm going to say X. What is my first value of X? It should be equal to 0, which generally speaking, it's X minimum, okay? So I'm going to write the first value to be equal to X minimum, and I'm going to freeze it, meaning that's not going to change. What is my second value of X? It is 0.01, which I can get by taking my first value and adding 1 step length to that. Like, if I were to write so here is my X. X equal to X min which happens to be 0 in this problem. What is my next point? I have to take this and add delta x, right? So this is nothing but x min plus delta x, second value. And what is my third value? That is the previous value plus delta x. So I'll call this say x0, I'll call this x1, x2. x1 is nothing but x0 plus delta x, x2 is nothing but x1 plus delta x, and what would be x3? Previous value x3 equals x2 plus delta x, sort of like adding the step length. So I can take the previous row, and to that I have to add the step length, and I have to freeze the step length, like press F4 so that you get those two dollar signs, and then press enter. Somebody should tell Microsoft they are not helping. Nobody asked for your help, get lost. All right, anyway, so you have x, and then you want to compute f of x. How do you compute f of x? You type in the formula or the large function I had, which I'll copy from my previous sheet. Oops. All right, can you punch in this formula? You've used Excel, you know how to do that. Minus 26 plus 85 times x plus or minus 91 times x squared plus 44 times x cubed minus 8 times x power 4 plus x power 5. I can just write f of x. I don't even have to call it LHS now. F of x equal to this. Please do this. Are we good? Is anybody not sure how to proceed? So what do you do next? You have a formula written. You can drag it to the next row. You get minus 25 something, and you want to increment this. So if you want to go on till say x max equals 1, you just need to drag it down to whatever point you need it. Yes. So let's go until like 1.00. Not that we need it, but we just have to. We can just go up to 1. Okay. And I'm going to make the decimal points. I'll make it 3 decimal points, or maybe 4. And then you drag this down to populate the values of the function all the way up to x equals 1. Are we together so far? Yes. So now you scan through the table and see where the function flips sign from negative to positive or positive to negative. That seems to happen between 55 and 56. So for those who are doing it on paper, here is your initial starting narrow range where you see a sign change. You can get more decimal points by doing more iteration. For those who are doing on Excel, the first step would be to add an iteration. First iteration, which will be the average of the two. And Okay, we are going to just ask questions and answer. This being negative, what does that tell? Where do you go next? How do you narrow down the range? 555 is negative. 55 is negative. 56 is positive. Between these two, right? Between 555 and 560. So add one more iteration. Second iteration, which is the average of 555 and 560 divided by 2, and the function's value is 0.009. 0.009. So now at 555 it is negative. At 5575, I'm sorry, at 5550 it's negative. At 5575 it's positive. So average of the two, narrow it further. So if I add one iteration, third iteration is the average of the two. Okay. So now 5563 negative, 5575 positive. You are within the last 12 10,000s. You are within the last 12 10,000s. Okay. So 63 75. Now let's add one more iteration. And now 5569 negative minus 0.002 and then 0.5575 0.009. If your error criterion was to get it within 0.01, within 1/100th of a percent, you are already there. You can stop here. If you want to get this to 1,000th, then you would proceed further and say fifth iteration would be between 69 and 75. So we see that it's between 69 and 72. That's narrowing it down to the last three 10,000s. Okay. So you can keep doing more iterations, but the idea is at some point you are going to get to an answer to 4 decimal points. So let's add one more. Sixth iteration. So it's now between 69 and 70. Okay. At one point, it will become inconsequential if you add more iterations because you are only interested in 4 decimal points. So this is between 69 and 70. So if you take 0.5570, here's an important aspect. Listen, if you say 0.5569 to 70, that sounds like a range. But if you look at the 6th and 7th iterations, this is 0.5570 and this is also the same, but if you add more decimal points, it will show up more numbers. So if you are just interested down to 4 decimal points, this is as any variation is only after the 4th decimal point. So you can write now a statement at the end saying x equals 0.5570, the 0 is important, 0.5570 with error less than 0.01, number 1. Number 2, why is the 0 important? Because if you just say 0.557, that has 3 significant figures. It means you are measuring something or calculating something down to 1,000th resolution. But when you say 0.5570, it means you are having access to information to the 4th decimal point. So there is significance to the 4th decimal point, and this has 4 significant figures. When you talk about measurements, you always say say time, for example. You have an analog clock which we used to have in this room. If you read an analog clock, how right are you, or how right can you be? If your eyesight is good enough to see the minute hand and the minute marks, you are down to 1 minute. You are either at 500 or 501. So your answer always has a resolution of 1 minute and an error of half a minute, 30 seconds. You are either right by 30 seconds, or you are leading by 30 seconds, or lagging by 30 seconds at most. If you take your digital watch, the one on your cell phone or your Apple watches, there you have a minute hand, you have a second hand, and you might also have a microsecond, like a millisecond hand. So there your resolution is even higher. Now, when you talk about significant figures, what is the number of significant figures on the minutes you read from a wall clock? Tell me. Your resolution is 1 minute. Forget the second hand. Just say it has minute hand and hour hand. How many significant figures can you get down?
Just one's figure, right? Like I have met.
Don't ask me, don't tell me something and ask right. You have to make a commitment. Commit. You can read 1 minute. What is the longest interval of time that can be read? 60 minutes or 59 minutes. Right? So when you report minutes, you can report 59 or 1. You can report two significant figures in 59 or 1 significant figure in 1. Okay. So the clock allows you to get 2 significant figures. Of course, some cases it's only 1, but some cases it allows you 2. Your digital clock, on the other hand, suppose you are reading 5 and then 0, 1 and then 30 milliseconds. You are getting additional significant figures. You are getting additional information which carries over as significant figures. One more example I'll give you. Please stop packing your bags. There is still 5 more minutes. Okay. Your car's odometer. How many significant figures does your odometer provide?
It increases with the distance you travel, because once you get past the decimal point, you're gonna add it.
You will have your first mile. Until you hit the first mile, it will keep reading 0. And you can add 9,999. Like you can be one shot of 100,000 miles and it will still read 999. So the most number of significant figures you get here is 5. Okay. If you have a balance, something to weigh items, okay, a mass balance. If the mass balance has a display, okay, that has, or it has a range, let's say up to 100 grams, okay, and it can give you 2 decimal points. That is, it can read 100.00. How many significant figures there are here? 5, because the information is all the way down to the second decimal point. You could have a measurement of say 10.1 grams on that instrument. It will be displayed as 10.10. Okay. You will notice that in many devices, when they cross a certain range, they will drop a decimal point because they have added one more place here. I don't know how many of you do bicycling. If you see the little odometer on your bicycles, the first 100 miles or first 10 miles, you will have 3.24. Okay, from 0, that is from 0.00 to 9.99, you have three significant figures, but 2 decimal points. The moment you hit 10, it becomes 10.0 to 99.9. Still maintaining three significant figures, but drop one decimal point. The moment you cross into the hundreds, you get 100 to 999. You still have three significant figures, but no information about the decimal point. So they optimize the number of significant figures, which is related to number of bits you use in an electronics device. But the idea is significant figures tell you how much, or not just about this measurement or this number, it also tells about the system which is producing these numbers. Anyway, coming back to decimal points and significant figures, you have 4 decimal points here. If I ask you to write this to 4 significant figures, what will you write?
0.5570.
0.5570, right? So we will write 0.5570 is 4 sig figures, 4 decimal points. If I ask you to write the same answer down to 3 significant figures, what will you write?
0.557.
0.557 has 3 sig figures. Of course, if this were a 5, you would round it off as 0.558 and write it as 3 sig figures. Okay? Remember this, if you have the decimal point, all the digits that follow here are significant. Before the decimal point, all the zeros that precede the number are significant. So if I write 1, a 0 before that, this has 2 plus 4, 6 significant figures. Okay? At least for this course, you should be able to present your answer rounded to a certain number of decimal points and containing a certain number of significant figures. So if you go to your textbook, I think if you see part one, there is an entire discussion on significant figures and rounding off, which I'm asking you to read because I'm expecting you to know that while you do talk. Okay, it won't be a direct question on that topic, but you'll have to know it in order to answer these other problems. Okay? All right, so that's 12:45. We'll meet on Tuesday. Have a nice day. Thank you.